Hello my friends and welcome back to the You Can Do TV channel. The Verdura Retaining Wall System by Soil Retention Systems, Inc. is a modular soil retention solution engineered for long-term structural stability and erosion control. It is designed for professional applications such as large retaining walls, channel walls, sound and screen walls, levees, and bridge abutments, as well as smaller residential installations. During installation, Verdura units are stacked and mechanically connected, then backfilled and compacted to create a reinforced soil structure. The open cell geometry allows vegetation to be planted directly within the wall, enabling root systems to integrate with the backfill and enhance overall stability. This plantable design improves drainage performance, reduces surface runoff, and supports environmental integration without compromising structural strength. The reconstruction of Lower Ray Drive follows a structured step-by-step civil engineering process designed to ensure long-term durability and performance. The project begins with the removal of the existing asphalt pavement. Excavators are used to break up the old asphalt, which is then loaded into trucks and hauled away for recycling. This reclaimed material is later processed and reused as Class 5 aggregate, supporting sustainable construction practices. Once the pavement is removed, work shifts to underground utility installation. New sewer, water, and storm sewer pipes are installed after excavating trenches to the required depths, which in this project reached more than 20 feet in certain sections. A crushed rock or gravel bedding is placed at the trench base, carefully leveled and compacted to provide uniform support. Pipes are assembled, aligned to precise grade, and then surrounded with additional aggregate to ensure stability. Manholes are installed at regular intervals to provide long-term access for inspection and maintenance. After pipe installation, backfilling begins. Soil is placed in controlled lifts of no more than 2 feet and compacted thoroughly at each stage. This step is critical to prevent settlement and protect the integrity of both the utilities and the future roadway. With underground work complete, the road is cut to final grade. The subgrade is leveled, compacted, and prepared to receive the aggregate base. In areas requiring additional structural support, geotextile fabric, or geogrid, is installed beneath the gravel to improve load distribution and stability. A layer of Class 5 aggregate is then placed, graded, and compacted to form a strong foundation. Next, concrete curb and gutter are installed along the roadway edges. After the concrete has cured, crews prepare the surface for paving. New asphalt is laid in multiple lifts, totaling approximately 4 inches in thickness. The first layer provides structural strength, while the final surface layer ensures smoothness and durability. Rollers compact the asphalt to achieve proper density and finish. The final stage involves placing topsoil along disturbed areas and completing seeding, restoring the surrounding landscape and marking the completion of the roadway reconstruction. Inside BGA Pile's production facility, strength is engineered long before a pile ever reaches the ground. The manufacturing process begins with caging, where pre-tensioned PC bars are precisely cut and welded into a rigid reinforcement cage. Accuracy at this stage defines alignment, load capacity, and long-term durability. Concrete feeding follows, combining carefully selected aggregates, cement, and performance admixtures. The mix is poured into rotating molds, while pre-tensioning is applied to the steel, introducing controlled internal stress that will later translate into exceptional structural performance. Timing and consistency are critical. Every parameter is closely monitored. The centrifugal procedure is where the pile truly takes shape. As the mold spins at high speed, centrifugal force drives the concrete outward, compacting it densely against the mold wall. Excess water and air are expelled, producing a high-strength hollow core section with superior uniformity. Initial curing begins immediately within the rotating mold. Next comes steam curing, performed under tightly controlled pressure and temperature. This accelerated curing process enhances early strength development, stabilizes material properties, and ensures consistent quality across every unit produced. In the final stage, the piles are demolded, allowing hydration to continue under optimal conditions. This step locks in strength, durability, and long-term performance. From steel preparation to final curing, each spun pile is the result of disciplined process control, designed to deliver reliability, efficiency, and confidence in demanding foundation applications around the world. December 10, 2025 marked a defining moment in the history of Polish road engineering. On that day, the tunnel boring machine Carpatka emerged at the North Portal, completing excavation of the first tunnel tube on the S19 Rzów Południe-Babica section. More than a breakthrough in rock, it was a breakthrough for the Via Carpatia corridor, a strategic artery linking northern and southern Europe. Stretching over 200 meters, the tunnel is being driven by the largest TBM ever deployed in Poland and one of the most powerful operating worldwide. Its cutting head spans more than 15 meters in diameter, while the entire machine weighs nearly 5,000 tons. Transporting Carpatka from Santander, Spain, to Babica was itself a national record in logistics. Once assembled on site, the machine advanced through the complex geology of the Carpathian Flysch, demanding constant monitoring and adaptive engineering. This tunnel forms part of a 10-kilometer expressway section that also includes 6 viaducts, 2 road bridges, and a grade-separated railway crossing, setting a new benchmark for infrastructure projects in Poland. Experience the 5th episode of Garaventa's construction diary for the Schildhornbahn 20XX project, featuring the spectacular installation of the rope shoes at Tower 3. Led by Chief Installer Reto Sigrist, the team shares rare behind-the-scenes insights into precision assembly, safety, and coordination at altitude. The episode highlights exceptional teamwork and shows how complex challenges are solved step by step in demanding alpine conditions. The Schildhornbahn 20XX project will deliver a state-of-the-art aerial tramway with a capacity of 800 passengers per hour, linking Stechelberg and Mürren. A major innovation is the fully automated, freight and baggage logistics system along the route. Above Murren, advanced Funnefour cableways will connect Berg and Schilthorn, offering outstanding wind stability and enabling compact, efficient station designs. Built for reliability, performance, sustainability, and year-round operation in environments. High above Saas-Fee, inside the heart of the Allalin Massif, Garaventa reached a defining moment in 2024 with the overhaul of the Metro Alpine at Felsken Middle-Allalin. After 4 decades of service, the original carriages had earned their legacy, but the future demanded a new standard of comfort and reliability. Delivered to the valley on low loaders and lifted by crane, the new vehicles began an extraordinary ascent. Suspended on steep gradients, carefully transferred across tracks, rotated, leveled and guided meter by meter, each movement required absolute precision. What followed was quieter but no less critical. Fine adjustments, electrical commissioning, safety brake setup, and millimeter-level alignment hidden from view. The work was complex, time-consuming, and unforgiving. Yet every step unfolded exactly as planned. When the tunnel doors closed again, little seemed changed to the eye. But inside, the Metro Alpine had been decisively renewed for the decades ahead. The Calasin Phase 2 project represents a rare leap in large-scale irrigation engineering. Unlike conventional pipelines used for oil, gas, or drinking water, typically narrow and elevated, this scheme introduces a 107-kilometer-long pipeline with an unprecedented diameter of 4.6 meters, buried underground across Madhya Pradesh. For the first time in India, water is pumped through a single pipeline to heights reaching 138 meters, demanding exceptional hydraulic precision and structural integrity. Sourced from the Indira Sagar Reservoir, water is transferred across river basins, overcoming complex geoclimatic constraints that make open canals unviable. The system relies on 4 major pump houses equipped with 45 high-capacity pumping units, each operating with independent motors to ensure reliability and control. To support construction, 4 dedicated pipe manufacturing yards were established, producing and rigorously testing each pipe through radiography and hydrostatic pressure testing. Once complete, the project will irrigate 275,000 acres and deliver drinking water to 270 villages, reshaping water security for the region through bold, first-of-its-kind engineering. At the Auhafen in Mutens, near Basel, a new landmark for agricultural logistics is taking shape. On behalf of the Finaco Cooperative, Marty AG Basel is constructing a silo block comprising 23 individual silo cells, each rising with remarkable speed and precision. To achieve this, the project relies on slip-form construction, a method perfectly suited to tall, continuous concrete structures. Once the process began, the formwork moved almost without pause, allowing the silos to grow by up to 4 meters every day. Concrete placement, reinforcement, and surface finishing were synchronized into a single, uninterrupted operation, running day and night. The technique minimizes joints, enhances structural integrity, and accelerates delivery without compromising quality. In the tight setting of the port, efficiency was essential. Through disciplined coordination and proven expertise, the silo block steadily climbed upward, transforming wet concrete into a high-performance storage facility designed to serve Switzerland's agricultural supply chain for decades to come. Since 1991, Trummer has focused on one core principle: creating robust steel mesh systems that stand between natural hazards and critical infrastructure. Engineered for extreme loads, these high-strength steel nets form the backbone of protection against rockfall, landslides, avalanches, and unstable slopes. Anchored directly into the terrain, the mesh systems absorb impact energy, stabilize loose material, and prevent progressive failure before it can escalate. Continuous research and development ensure each system performs reliably in real-world conditions. Through projects such as the Najima initiative at the Erzberg mine in Styria, Trummer has refined mesh geometry, wire strength, and anchoring concepts under some of the harshest environments imaginable. The result is a durable, adaptable protection system, designed not just to resist nature, but to control it safely and predictably over time. Building a 3D printed home begins with digital design. Architects create a precise 3D model that integrates structural, electrical, and plumbing requirements. Once the foundation is prepared, a large-scale printer extrudes a special concrete mix layer by layer, forming walls directly from the digital plan. Openings for doors, windows, and utilities are printed in place. After printing is complete, the roof system, insulation, wiring, plumbing, and interior finishes are installed using conventional construction methods. This approach reduces material waste, shortens build time, and enables highly accurate, repeatable housing construction. At Zurich Central, the name says it all. This is the city's beating heart of public transport, where more than 45,000 passengers move through every single day. In the summer of 2017, that heart had to be opened and rebuilt without stopping the city around it. Worn tram tracks were removed, street surfaces renewed, and an entire traffic system re-engineered under extreme time pressure. Over 450 meters of new track were installed, along with 13 switches and 7 rebuilt intersections. Curve radii were widened to allow trams to pass more smoothly and at higher speeds. 4 tram stops were rebuilt, platforms extended, and bicycle routes improved, transforming Central into a unified, modern urban space. The most critical phase came in early July. From July 8 to 11, Central was completely closed to tram and bus traffic. Work continued around the clock. At peak moments, nearly 400 workers and 1,000 tons of machinery filled the site. In a single weekend, 500 cubic meters of asphalt and concrete were removed, equivalent to 167 truckloads, then recycled and rebuilt from the ground up. Every operation was tightly synchronized. While demolition continued in one area, new track beds were already taking shape nearby. Excavation reached 70 centimeters deep, followed by geotextile layers, gravel beds, utilities, drainage systems, precision-aligned rails, and hundreds of nighttime welds. Concrete was poured in stages, locking the rails into position before final surfaces were restored. All work had to be completed before Zurich Street Parade in August. By mid-month, testing was finished, trams returned, and Central reopened, rebuilt, reinforced, and ready for the future of urban mobility. Each year, Hong Kong International Airport moves millions of passengers across continents. To shorten the distance between Terminal 1 and the North Satellite Concourse, a new connection had to be created, one that would operate airside, above active taxiways, without disrupting daily operations. The result is a 200-meter skybridge, now the longest of its kind in the world. Fabricated in mainland China, the 100-ton structure arrived with no margin for delay. A narrow tidal window demanded speed, so a custom quick-pin release system allowed sea fastenings to be removed within minutes. From there, the challenge shifted to land. Transporting the bridge just 3.5 kilometers required absolute precision inside one of the world's busiest airports. To meet the constraints, Mammoet deployed a self-propelled modular transporter fitted with the MegaJack 5200 system, used in this configuration for the first time. The bridge was lifted, stabilized, and moved overnight across taxi lanes using 264 axle lines, navigating tight clearances and gradients with millimeter control. Once on the apron, the structure was raised to 46 meters using strand jacks inside 4 towers, then shifted laterally into position before final lowering. Working around the clock, the team completed installation within a critical 9-day window, just in time for the Lunar New Year surge. The skybridge now stands as a seamless link in Hong Kong's global gateway, engineered for speed, safety, and uninterrupted flight operations. At a controlled pace of roughly 5 meters per minute, the launcher moves longitudinally, carrying the beam to its span. Transverse movement on integrated rails allows precise lateral alignment before the beam is gently lowered onto its bearings. After completing a span, the launcher advances itself to the next, supported at 3 points as it glides forward. This sequence repeats until the bridge is complete, efficient, precise, and engineered for places where access is the greatest challenge. Zurich Airport operates at the center of global air traffic, where continuity is non-negotiable. With an average of 720 takeoffs and landings each day, more than 25 million passengers a year, and over 25,000 jobs on site, the airport is a critical engine of Switzerland's economy. That reality defined the challenge behind the rehabilitation of runway 1430 seconds. Commissioned in 1976, the 300-meter runway had endured decades of intense loading. Its central strip required complete renewal, but without interrupting flight operations. After years of planning and approvals, the main rehabilitation phase began in March 2014, executed entirely at night. Each work window lasted just 8 hours, unfolding while daytime air traffic continued. Across 49 tightly sequenced stages, some stretching up to 90 meters, crews replaced aging concrete slabs with a modern 2-layer asphalt system. As soon as the final aircraft departed each evening, more than 100 workers and 80 machines moved onto the runway. Mobile noise barriers were installed first to protect nearby communities, then demolition began. 2 90-ton excavators broke out 30-centimeter concrete slabs, removing up to 500 tons of material per night. While demolition continued, milling machines trimmed the stabilized foundation to accommodate the thicker asphalt structure. New conduits for runway lighting were installed, followed by the arrival of low-temperature asphalt just hours before dawn. GPs controlled equipment, placed and compacted the base and binder layers with millimeter accuracy, while synchronized rolling ensured uniform density and strength. Parallel crews upgraded the centerline lighting system, using fast-curing high-performance concrete, achieving full operational strength by morning. 1 hour before the first landing, machines cleared the runway, markings were applied, surfaces cleaned, inspected, and approved. By 7 a.m., the runway was back in service. A final surface course extended durability and enhanced drainage, securing safe operations for decades. Through precision planning, flawless coordination, and minute-by-minute timing, runway 1430 was rebuilt, without ever grounding the airport, ready to serve another 30 years of global aviation. Deep inside the Glattalp hydropower plant, work is underway in one of the most demanding sections of the facility, the incline shaft. The task is the removal of the old pressure pipeline and the installation of a new one, an operation planned almost entirely through detailed simulation. Every meter of the shaft was digitally captured, analyzed, and mapped before a single component was moved on site. The pipes themselves are standard 2-meter sections, but the environment is anything but standard. At a 45-degree incline, every operation requires careful securing and strict safety discipline. Conditions are tight, access is limited, and time is critical. Completing a full rehabilitation within a single year is ambitious, yet the team has found its rhythm. Early challenges are behind them, progress is steady, and the project is firmly on track. High above the Glattalp hydropower plant, work on the incline shaft entered a critical phase with the installation of the new winch elevator. Positioned near the mountain station, the operation centered on flying large mechanical components into place by helicopter. Every lift demanded tight coordination between the pilot, project management, and ground crews. Load weights, flight paths, landing zones, and weather conditions were checked repeatedly, with constant radio contact maintained throughout. The challenge for the pilot was precision, placing heavy components onto a confined platform with limited visibility and strong downdraft from the rotor wash. Safety rules were absolute. No personnel beneath suspended loads, all areas secured before approach. Favorable weather finally aligned, allowing the lifts to proceed smoothly. Compared to the old system, the new winch elevator delivers higher payload capacity and a redesigned drive located at the top, reducing cable length and simplifying installation. After earlier delays, the helicopter operations were completed efficiently, marking a major milestone in the shaft rehabilitation. IUCS Group has delivered precast solutions for stormwater management and erosion control, with its erosion control mats recognized for high structural performance. Begin by preparing the base in accordance with IECS or project specifications, shaping and compacting native material to at least 98% SPMT and removing all debris. Installation starts at the downstream end and progresses upstream. Place mats tightly, maintaining gaps no greater than 2 inches. Clamp adjacent mats together at the looped ends, as close to the base as possible, and tuck excess loops beneath the blocks. Provide a 1 to 2 block key-in at both the crest and toe of the slope. Where mats interface with head walls or concrete structures, lag them using stainless steel hardware and grout with 25 MPa concrete to ensure structural continuity and erosion resistance. At the heart of northeastern Turkey, Yusufeli Dam continues its steady rise, reshaping the landscape with one of the country's most ambitious hydroelectric projects. As the structure climbs higher, efficiency and precision become critical. Concrete placement is carried out using a cable crane system, delivering material across steep terrain where conventional access is impossible. Complementing this approach, a conveyor belt system ensures a continuous, controlled flow of concrete to the pouring zones. Together, these systems reduce handling time, improve placement accuracy, and maintain consistent concrete quality at height. The synchronized operation allows large volumes to be delivered safely while keeping crews and equipment clear of hazardous zones. Day after day, layer by layer, the dam advances upward, driven by engineering solutions designed for scale, reliability, and speed. Yusufeli is not just being built, it is being methodically assembled through technology that turns geography from an obstacle into an advantage. In February 2018, Manchester Airport entered a defining chapter with the launch of its £1 billion transformation program, the largest single investment in its history. Designed to future-proof one of the UK's busiest gateways, the project set out to expand capacity, streamline passenger flows, and elevate the travel experience. Central to the plan was the expansion of Terminal 2, creating a modern, light-filled hub capable of handling millions more passengers each year. All of this unfolded, while the airport remained fully operational, demanding careful phasing and precise coordination. Construction progressed alongside live aircraft movements, security operations, and daily passenger traffic. More than a building project, the transformation represented a strategic shift, preparing Manchester Airport to compete on a global stage, support regional economic growth, and deliver a smoother, more connected journey from curb to gate for decades to come. The old foundations that once supported the pressure pipeline are being broken out and completely renewed. Using a specially modified demolition trolley, crews chisel away the concrete, section by section, before excavators remove the debris. The real challenge is control, keeping the trolley stable, avoiding hang-ups, and working safely in tight conditions, where access is limited and the concrete remains stubbornly hard. Meltwater adds another layer of complexity. Regular water barriers and continuous pumping are required just to create conditions suitable for concreting. Despite the obstacles, the atmosphere on site is one of focus and determination. Early startup issues have been resolved, workflows are now smoother, and progress is steady. It's demanding work, but also deeply rewarding, and a source of genuine pride for the team involved. In Interlocking, France, a failing roadside slope threatened county road stability. Instead of sheet piles, the interlock system was selected for faster, more economical installation. With geogrids and 300 interlock anchors installed over 100 meters in just 3 days, the solution stabilized the embankment efficiently without heavy equipment. Drainbase is an engineered, water-buffering tile system designed to create a fully permeable base for artificial turf applications in gardens and roof terraces. Installation begins with preparing a stable, level subbase in accordance with project requirements. Drainbase tiles are then laid in a continuous pattern, ensuring tight alignment. Where required, tiles are cut precisely to fit edges, corners, and penetrations. Drainbase caps are inserted to secure and stabilize the system. Once the tile field is complete, artificial grass is rolled out evenly over the surface, tensioned and trimmed. Final drainbase caps are inserted to Rising from reclaimed sea, Dalian Jinjiawan International Airport is redefining scale. Spanning more than 20 square kilometers, this USD 4.3 billion mega-project relies on deep foundations, 1.6-meter piles, driven beyond 90 meters, installed with XCM GXR 580 rigs and Drillmaster casing for speed, stability, and precision beneath of the world's largest reclaimed airports. To unlock the future 3-runway system at Hong Kong International Airport, construction began beneath the sea in August 2016. The first challenge was forming 650 hectares of new land, much of it resting on soft, contaminated marine mud. Instead of dredging, engineers turned to deep cement mixing, a method that strengthens the seabed in place while protecting surrounding waters. After geotextile placement in a 2-meter sand blanket, DCM rigs drilled deep, injecting cement to transform weak mud into solid structural columns. Every movement, material flow, and mixing ratio was monitored in real time. Multiple layers of silt curtains, continuous water quality checks, and trained dolphin observers ensured environmental safeguards remained intact. With 250,000 cement clusters created around the clock, this became one of the world's largest marine applications of DCM technology. By November 2024, construction of the new Nissan Stadium had reached a visible turning point. Standing on the mezzanine above field level, crews were forming the massive elevated slab that will support the structure above. Hundreds of concrete workers advanced in coordinated sequences, meeting at the southeast corner. Nearly 2 million square feet of slab were taking shape, laying the foundation for the steel superstructure and roof to follow. In Turin, the SMAT group rehabilitated a central sewer beneath Strada del Drosso using no-dig Dura.cl discrete pipelining technology. Supplied by Società del Gray, part of the Steinzeug-Caramo group, the solution renewed 440 meters of pipeline at depths of up to 10 meters, minimizing surface disruption while delivering a fast, durable, and highly controlled rehabilitation process. This fully automatic brick machine is engineered for high-volume, precision-driven production, delivering up to 30,000 bricks per day with consistent quality. The process starts at the box feeder, which regulates raw material flow into the system. A crusher roller and fine roller then break down and refine the material to achieve uniform particle size. The prepared mix moves into the mixer extruder, where moisture and additives are blended thoroughly before extrusion into a continuous clay column. The brick cutting machine slices this column into perfectly dimensioned green bricks at high speed. Finally, the automatic brick stacker organizes the bricks efficiently for drying and firing. Together, these integrated systems create a streamlined, labor-saving production line built for industrial-scale reliability and performance. The interlocking brick production process for the Lotus model is designed to deliver high-strength, precision, and rapid construction efficiency. Using a specialized mold system, raw materials are compressed to form bricks with accurate interlocking profiles. These profiles allow bricks to fit tightly without excessive mortar, improving structural stability and alignment. The Lotus model emphasizes uniform dimensions, smooth surfaces, and consistent load-bearing performance. Automated pressing and controlled curing ensure each brick meets quality standards. This system supports faster wall assembly, reduced material waste, and durable masonry structures suitable for residential and commercial applications. This tutorial introduces how door and window openings are formed using my IB compressed interlocking bricks, a system engineered for precision and speed on site. Openings are planned directly into the wall layout, allowing the interlocking pattern to guide alignment from the first course upward. As the wall rises, specially arranged bricks maintain load continuity while clearly defining the opening edges. Lintels are integrated seamlessly above doors and windows, distributing weight evenly without disrupting the interlock. Because the bricks lock into position mechanically, courses remain level and plumb, even around structural interruptions. Minimal mortar is required, reducing curing time and keeping dimensions accurate. The result is a clean, square opening ready for frames without extensive cutting or rework. This method not only improves construction efficiency but also preserves the structural integrity of the wall. With MyIB technology, door and window openings become a controlled, repeatable process, combining simplicity on site with the strength and durability expected from modern masonry systems. At Stuttgart 21, construction has entered its final and most symbolic phase, installing the last meters of track in the future main station. What was once an open construction hall is now being transformed into a functioning railway hub. After re-exposing the pre-built track troughs, crews construct the load distribution layer to absorb train acceleration and braking forces. Reinforcement is placed, concrete is mixed on-site, pumped in, vibrated, and left to cure. Once hardened, the slab track system follows. Sleepers are positioned, rails are lifted in with a dual-mode vehicle, and the alignment is set with millimeter precision by surveyors. Final concreting locks the system in place. Section by section, nearly 3.8 kilometers of track are being installed, turning raw structure into a station ready for high-speed rail. How quickly and efficiently the record Holtzmann thermosystem floor slab insulation formwork can be installed and processed on-site. Designed as a complete, integrated solution, the system combines thermal insulation, permanent formwork, and a precisely engineered step profile that complies with DIN 18195 requirements for protection against rising damp. The process begins with the accurate placement of the first insulation panel, forming the geometric and thermal foundation of the slab. The prefabricated system legs are then attached, creating a stable perimeter formwork that ensures dimensional accuracy and reliable edge insulation. At this stage, the longer insulation panels are laid first to define the primary edges of the floor slab and ensure continuous thermal separation along the perimeter. These extended panels create a stable, uninterrupted insulation line, reducing thermal bridges and improving overall energy performance. At each corner, prefabricated corner elements are installed to lock the system into position. Once fixed, the perimeter becomes rigid and self-supporting, providing a reliable base for the subsequent installation steps and ensuring clean, straight slab edges during concreting. Thanks to the lightweight yet rigid construction, alignment is straightforward and requires minimal corrective work, even on larger slab geometries. Once the formwork is fully assembled, the slab is ready for concreting. In this application, steel fiber reinforced concrete was used. This advanced concrete mix distributes tensile forces evenly throughout the slab, allowing the project to dispense entirely with conventional reinforcement, such as welded steel meshes. After the concrete has been poured and properly compacted, the system continues to deliver value. Once curing is complete, the integrated step profile can be removed quickly and cleanly. This exposes a precisely defined edge, providing ideal conditions for applying the waterproofing layer against rising moisture in accordance with relevant standards. The system demonstrates how modern, well-engineered building components can significantly improve efficiency, precision, and overall build quality in contemporary floor slab construction. Silca Tempo is a construction system designed for the fast and efficient building of single-family houses without compromising structural performance. It is based on large-format calcium silicate blocks with a high compressive strength of 20 megapascals, providing excellent load-bearing capacity and very good acoustic insulation. Thanks to the large block dimensions and a high level of work mechanization, wall construction time can be reduced by up to 50%. A two-person crew supported by a dedicated mini crane is capable of erecting up to 50 square meters of wall in a single working day. The showcase project involves a large 300 square meters single-family house, where ground floor walls reach heights of up to 4 meters, and the entire two-story structure is built using Silca Tempo technology. The Spider mini crane with a 250 kilogram lifting capacity ensures precise and safe installation. Rising at full speed, Yusufeli Dam is taking shape as the world's highest dam of its type. Construction began on December 21, 2012, advancing through some of the region's toughest rock. Carefully controlled blasting was used to carve foundations, driving progress on this landmark hydropower and dam project. With a height of 270 meters, the Yusufeli Dam and hydroelectric power plant ranks as the world's third highest in its category. A critical phase of the project was the transportation of heavy construction machinery to the remote site. Excavators, cranes, tunneling equipment, and oversized components were moved through narrow mountain roads, tunnels, and temporary bridges. Detailed logistics planning ensured safety, timing, and minimal environmental impact. Specialized trailers, convoy coordination, and reinforced routes were required to handle extreme loads and steep gradients. The successful delivery of these machines enabled continuous construction progress and demonstrated advanced engineering, logistics management, and cooperation under challenging geographical and climatic conditions during complex high-altitude operations. At Yusufeli Dam, construction reached a defining milestone with the placement of the 3 millionth cubic meter of concrete. Day by day, the dam body continues to rise, shaped by a disciplined, high-tempo pouring operation. On average, 400 cubic meters of concrete are placed daily, carefully sequenced to maintain strength, temperature control, and structural integrity. Working primarily during daylight hours, crews advanced the structure in measured vertical stages, climbing past 100 meters, then 200 meters, each lift bringing the project closer to its final height. Every pour is planned with precision, from batching and transport to placement and compaction, ensuring consistency across the massive dam body. Reaching 3 million cubic meters is more than a number. It marks the scale, endurance, and coordination behind one of Turkey's most ambitious hydropower projects, steadily transforming engineering effort into a landmark structure carved in concrete. Rising from the steep valley of the Koru River, the Yusufeli Dam stands as one of the world's tallest megastructures and a defining achievement of modern dam engineering. Located 70 kilometers southwest of Artvin in Turkey's eastern Black Sea region, the 275-meter-high dam anchors the largest reservoir in the Koru Basin, capable of storing more than 2 billion cubic meters of water. From the outset, nothing was left to chance. Detailed three-dimensional geological and geotechnical models shaped every design decision, ensuring the dam body could safely transfer immense loads into the surrounding valley slopes. More than 560 kilometers of grouting were drilled to stabilize foundations, while the extreme terrain demanded an unconventional solution for access. 2. 420 meters of spiral transportation tunnels connecting different elevations during construction. Concrete placement began in July 2018, advancing at an average of 4,500 cubic meters per day and peaking at over 8,000. By mid-2021, 4 million cubic meters had been placed. Despite the demanding geography, impoundment began in November 2022, and electricity generation followed in 2023. Today, Yusufeli produces enough clean energy to power 2.5 million people annually, while also boosting efficiency at downstream dams by regulating flow and trapping sediment. Beyond energy, the project reshaped an entire region, delivering new infrastructure, roads, tunnels, bridges, and a modern resettled city. Yusufeli is not only a dam, it is a statement of scale, precision, and long-term national engineering vision. The second phase construction at the Yokaichi Wastewater Treatment Center in Mie Prefecture highlights a major coastal defense upgrade. As part of the shoreline expansion works, a new seawall is being constructed 100 meters seaward of the existing embankment to enhance protection against storm surges and wave action. The project features the installation of specialized wave return blocks on the new seawall, designed to deflect incoming waves and reduce overtopping. Their modular design allows for rapid placement, significantly improving construction efficiency and contributing to a shortened project schedule while maintaining robust coastal resilience. Areger AG carried out the controlled demolition of the Hagnau Tunnel in Mutens within a tightly scheduled 80-hour window. The 88-meter-long tunnel structure, featuring concrete sections up to 2.7 meters thick, was systematically dismantled, along with the supporting frame system and retaining walls. In total, approximately 500 tons of reinforced concrete were removed. The tunnel opening measured 3.10 meters in width, demanding precise, high-force demolition techniques. To meet these requirements, Areger deployed its most powerful large excavators, including the AREX, equipped with the new MD3000 concrete crusher. With a jaw weight of 29 tons and a carrier weight class of 30 tons, the equipment delivered the necessary power, control, and efficiency to complete the project safely and on schedule. In ancient stoneworking, one common cutting technique involved drilling a series of aligned holes along the desired fracture line of a rock block. Metal wedges or wooden dowels were then inserted into these holes. By hammering the wedges or soaking wooden pegs with water to make them expand, controlled tensile stress was created inside the stone. This gradual, evenly distributed force caused the stone to split cleanly along the prepared line with high precision.